Right. I would like to welcome our next speaker from GE Intelligent Platforms, Mr. David Adams. He's a market development leader.
Well, as Monty Python says, and now for something completely different. So GE Intelligent Platforms really goes cross-vertical. So we are involved in oil and gas, in power generation, in mining, and aviation. I'm here to speak to you about the industrial internet and how that applies into your life. I was glad to see Entergy participating. They were one of the early adopters of technology like this, and have found a great benefit for it. You know, your goals, whether you state that goal as NOx reduction or reliability, megawatt production, cost, you want to see your performance go up and your surprises go down. It's a pretty universal item. And these days, we have our context fluctuating, and we have lots of data about that context, but how do we make sense of it all? And really, what predictive analytics helps you zero in on what's important for you right now. What should your people pay attention to? I think I was exposed to a study, it's maybe about 4 years old now, but I don't think it's changed too much, that the average power plant control room operator gets 800 alarms a shift, which essentially means they get zero, right? How do they figure out what to do from all of that? So by helping identify the key points that should be taken care of in a proactive way versus a break-fix idea, you can drive focus and return on investment. Whether you're converting a plant that's now operating, you know, it was designed for base load and now it's going to cycle, so it's going to operate differently. You need help to set priorities for that equipment, or whether it's just a plant that's aging and going out of service, or even infant mortality on a new plant. So for those who aren't familiar with this curve, it's called a P to F curve, and it's when equipment can operate at its potential. And even though, you know, this is drawn as a nice smooth curve, they're not always nice and smooth like that, but over time a piece of equipment will give precursors. But most of the protection equipment on the right-hand side that will shut the equipment down for safety reasons, that lets a deviation go to a certain level, move back to the left a little bit. All of the diagnostics that many people create, whether they're specialists in a particular type of equipment or a particular technology like vibration, acoustics, thermal, those are meant to really help diagnose the problem, not to find it earlier. So what we're talking about today is the precursors to give you foresight along with the insight. And many times when you try to take those protection and diagnostic technologies and force an early warning out of them, the amount of manpower required to do that is incredible. If you think about today, you can get a Google map on your phone and it'll tell you where the traffic is and where it isn't and where to go. Okay? To some extent, the industrial internet is providing us the ability to do very similar things in the management of our equipment. Before I get into the concepts, I'm just going to kind of get granular for a minute. So this is an example where two people in our monitoring center advised a customer that their bearing was running at 185 degrees Fahrenheit. And the normal response before being exposed to this type of technology is like, who cares? My alarm limit on that bearing set at 225. We're like, no. For how hot it is, for how hard you're running, for all the other contexts in the plant, it should be at 185. So what they did is they went out and found out, it's kind of funny, a forklift truck had run into the piece of equipment and had pinched a lubrication line. So they were able to find the problem before starving the bearing for lubrication, before causing any damage, in a proactive way. And that's really a lot of what I'm here to talk to you about today is, as you're talking about really big strategic changes in how you produce electricity, a strategic change from reactive to proactive, a strategic change in your data strategy. Many times, these decisions are pushed down to a level where they don't get really done at a broad level, and I would, again, congratulate Entergy for having made a strategic decision across their fleet for predictive technology. This is one, I think I missed one. Yes. So this was a vibration example where a motor-driven reciprocating compressor was operating at 18% of its vibration alarm limit. Again, who cares? It's 18%. No, it should be operating at 13%. They went out there, they found the bolts were starting to back out of the motor, holding it down to the skid. Would you rather just tighten the bolts, or would you rather wait until the motor's hopping off the skid and you've bent the shaft? You know, and for producing well, producing reliably, especially as you're changing plants into new operating regimes, I think those things are important. This is an example of a non-mechanical failure where it was a failure of performance. Someone left a valve open, so they were venting steam to the atmosphere instead of producing megawatts. And because it was not part of the normal operating regime of the plant, we were able to catch it. So how do we do that and make it easy? First of all, I'll make a little joke. So, you know, what's that shape, right? The guy on the left says, I love circles, right? Guy down here says, that's a triangle. Go over here, they're full of it. It's a square, right? Somebody says, I don't know. And then there's always somebody who's going to make up his own story. So that can be applied to condition monitoring, remote monitoring, diagnostics, because many of these things today are point solutions, not a holistic look. And when you're trying to go after high-level outcomes, improved availability, world-class reliability, you've really got to look at this as a portfolio solution, not a point exercise. So you can really look at it like a vitamin pill, and the vitamin pill should contain both when and what. And predictive analytics will really help you with when, okay? And there are, well, yeah, I guess there are some formatting things going on. Predictive analytics and things like vibration can go across many different types of equipment. You get OEM deep dive knowledge, whether it's from us or another company. They know their equipment best, and they're often the best people to advise on what to do once you've got the flag to do it. We'd like to work with those other companies, whether it's a GE company or another company, and really create a merged service rhythm so your team gets a ongoing sense of when to do things and what to do. If we get very sort of down into the engineering of it, a lot of things are at the level of actual value analytics, rule-based alerts, you know, the whole science of vibration could be considered signal processing. Physics-based analyses, there's a lot of thermal performance and optimization. There's also a lot of failure pattern matching for trip diagnostics and case-based alerting. Talking about really wrapping predictive diagnostics not only on the major assets that people have done those traditionally on, but also your balance of plant, valves, lube oil systems, filters, heat exchangers, to keep you aware of what's going on. You know, some of our customers have said, we can deal with anything we don't know. The stuff that keeps us up at night is the stuff we don't know about. And having a data strategy, having an overarching approach is really about keeping you aware of what's coming down the pike so that you can manage it. You know, several of these markets have really enjoyed the application of this technology. If anybody flew here on Delta Airlines, those engines sent a data burst during takeoff, cruise, and descent. And then the signal was sent back on whether that plane should be allowed to take off again. And the first year that happened with Delta, the number of times the pilot got up in the air, said something doesn't feel right, and went back to base was cut in half. That was the first year, with really no upgrading of the whole fleet. That happens over time. In Power, there's an article in Power magazine, I think it dates from 2008, called The Big Catch. Again, that was Entergy. And I think at the moment we're monitoring about 30 to 40% of the megawatt capability in North America and a fair chunk overseas. So this is a technology that you should look at, again, for that overarching strategy, especially as you're going to change a plant out and invest big dollars in making it a gas-fired unit or other. Make sure you've got your data strategy to run that plant well, the way you want it run. Oil and gas and mining both are enjoying the technology as well. When it's data-driven, then it's any OEM and any piece of equipment. It's not tied into a specific, I guess I'll probably use the term point solution too often, whether that is a particular technology solution or a particular OEM solution. You guys don't care whether one piece of equipment or the other piece of equipment has stopped you from operating today. You want to be operating today. You want to see the whole picture. To use a few of the math buzzwords, in thermal modeling, you should definitely be up here in the area of first principles. There are some good uses for parametric modeling. For understanding when, you should go take a look at things. Non-parametric modeling is really what you should be using. We happen to use a flavor of that called similarity-based modeling, but a lot of people can throw around a lot of math buzzwords, neural networks, all of that. Really, this is why you care, okay? Is we can have lots of people sit around and create fancy equations to match the data, but which red line would you rather use to predict the blue dots? Right? It kind of gets down to that simple, that people who are doing curve fitting, and in certain areas, like I said, curve fitting's the right thing, like thermal performance. But there are limits to how much you can do there. When you go to non-parametric modeling, you can really understand the data from your piece of equipment in your operating context, the way you run it. Because from a fleet standpoint, you don't really care if 5% of your pumps are going to have a problem in the next 6 months. You want to know which one, right? How's pump number 48 doing? And that's why you really have to match the data for each individual piece of equipment and get that actionable knowledge, not just nice to know. What percent of my pumps are going to fail this year is a budget question, not an operating question. Which pump is an operating question. So, as I mentioned, a lot of people and a lot of systems really depend on thresholds. And so how do we create that early warning? We relate all of the variables together. So pressure, temperature, vibration, load, all of the various things. The data modeling technology can handle hundreds of variables. Our normal data model is usually 50 to 100 pieces of data in each model. An average combined cycle plant, I know off the top of my head, probably has 5,000 to 7,000 sensors. We probably look at 1,000 to 2,000 of those. So we break that up into 20 to 30 data models, and that make engineering sense and that create that early warning. So by doing that, we can put a dynamic window around each signal, and when it leaves that dynamic window, we deliver time to you. This technique delivers time. That one I'm probably going to skip past. It's essentially a high-end version of matrix math. And again, it can handle any type of equipment. So when you get into carbon capture equipment, how are you going to monitor those, right? You've never run that piece of equipment before. Well, we can drink in the data from that, understand the operating context, and then give you actionable intelligence for a piece of equipment that you really don't know. And we always, have the actual pattern. We make an estimate of what it should be if the equipment is running correctly, and then by taking the difference between them that we call a residual, we take all signals back to zero. So it's 5 degrees hotter than it ought to be instead of it's at such and such a temperature, which allows your folks to make decisions a lot faster. The average vibration analyst, if you got a signal from your vibration signal today, or your vibration system today that says you ought to go look at something, they might spend between 4 to 6 hours normalizing the data to figure out if it's worth further investigation. That can all be done so that your experts can be applied more productively. None of you, I think, have expanding cores of experts, right? The knowledgeable workforce is aging. You have pressure on operating budgets. You want to use those people as efficiently as possible. We do try to keep it real for operators. We kind of say blue is true and green is good. And when the two of those separate, that's when you ought to take a look. So the green is the data science estimate of what it should be if the plant was operating on a healthy basis, and blue is the actual. Oh, that one got really messed up with the format. I'll skip it. So we take the equipment sensors, we apply the data technology and engineering knowledge to it, and that creates personalized empirical models for each piece of equipment. So between serial number 3 and serial number 4 on the same concrete slab, if one of them, I'm an old pump guy, so I think in terms of pumps, okay? So if one of them has 5 diameters of straight pipe in front of it, and the other one has 10 diameters of straight pipe, those two operate differently. And even if they had the same numbers of, the same length of pipe in front of them, 6 months from now, they will operate as individuals. Big pieces of equipment are individuals, and that's why it's really important to characterize each piece of equipment without spending huge amounts of your engineering time, but to have the data science characterize each piece of equipment as an individual. Can then run through diagnostic signatures built by subject matter experts, ours, yours, others, and really what that delivers is a dashboard that will tell you what's important, and then for each specific incident, so it's kind of exception driven. Again, you remember that arrow in the beginning saying, look here. So you'll understand what contributing factors there are, where it is. In this case, this is a gas combustion turbine. It says, believe you have a problem at the inlet filter. The apparent cause is icing, and the priority is 3. So the priority scheme is kind of, you look at it this hour, this shift, today, this week, or keep an eye on it. And you know, there are various systems that do this out there. Certainly, we like ours the best, but I think that the point here is really to have a data strategy that helps you be exception-driven in a proactive, early warning kind of way. We also find it's extraordinarily important to not just throw technology into the operations. If you have the people who operate the technology have to have experience and have to have relationship. Many people do this in a remote center, or they might hire it as a service, but having those experts who have the technology at their command, but having them have relationship on the plant floor means that something will get done. It won't just be an email in somebody's inbox that got ignored. So there's a real experiential and human component to making your operations as efficient as possible. And here's an example of working with one of those point solutions. So in the historian of a plant, there might be a variety of information around a journal bearing that's available. But when we connect up to the vibration system, we can get amplitude, phase, DC gap. And that allows us to do some pretty advanced vibration calculations, including orbit precession, ellipticity ratio. And we can put all of that into that data modeling engine I talked about. And what it means is that when we deliver a look here, we don't just have to say local bearing problem. We can say, we believe you have a misalignment or you have a subsynchronous rub. we can give a great head start to your experts who are going to determine what to do about it and when. But we can save them a lot of time. That one got messed up a little bit. Similar thing about startups. We can analyze startups, and I'll bet that any plant that converts from coal to gas is not going to start less, right? You're already cycling coal plants far more than they had planned on it as a design, and that's just going to continue. So really tracking your startups, being able to compare startups, being able to see the things that will trip you 2 or 3 starts from now instead of tripping you this current start, and then it's a scramble to react. Certainly, there's lots of information out there on what the business case is for doing a data strategy and predictive analytics. And a lot of it is in maintenance expense reduction because you can fix things cheaper if you find it earlier. But there's also a big revenue model impact that if when you want to cycle that plant and you want it to start and you dispatch it and then it doesn't perform, you've lost revenue. So again, I would encourage you that as you look at all of the things that have been talked about here today, restructuring gas versus coal and all of that, that you want to build in flexibility in your decision making by learning about things earlier. And with the data overload, GE is definitely investing a lot in the industrial internet. I think the industry is following us, and as an industry talk rather than a product talk, I would definitely say you should all be thinking about your data strategy as you also think about your fuel strategy. Okay? Any questions?
Any questions?
I've stunned you into silence.
Thank you very much, David. We've got a 30-minute break, so please grab a coffee, and we'll be back here in 3:30. Thank you.